Hello, my name is Ricci, and I'm going to be talking about chemical reaction equilibria. Chemical reaction equilibrium is an important aspect of thermodynamics. Given the conditions of a system, mainly temperature, pressure, and composition, the likeliness of a reaction to proceed, as well as how much product will be formed at equilibrium, can be determined. An important assumption, however, is that an infinite amount of time is allowed to pass. This is where the study of thermodynamics differs from that of reaction kinetics. In order to characterize chemical reactions at equilibrium, a constant known as the reaction equilibrium constant, K, is calculated. As you can see from equation 1, this constant is determined by the Gibbs free energy of reaction for the system, the gas constant, R, and temperature. The Gibbs free energy of reaction is determined by finding the sum of the Gibbs free energy of formation of each species multiplied by its stoichiometric coefficient. However, a common problem encountered when trying to calculate the equilibrium constant is that Gibbs free energies of formation are often listed at 298 Kelvin. For systems at other temperatures, equation 2 can be used to relate the equilibrium constant at 298 Kelvin to that at any temperature in Kelvin. Another important assumption is being made here, which is that the enthalpy of reaction, which, similar to the Gibbs free energy of reaction, is the sum of enthalpies of formation multiplied by their stoichiometric coefficients, is relatively independent of temperature. This is often done to make the problem simpler, as determining the enthalpy of reaction at any temperature utilizes a much more complicated equation. An application of this concept and method can be seen in many industrial processes. For example, a good case study is the production of lime from limestone. Lime is a widely used material in industrial processes, especially in iron and steel production, paper production, and water treatment. It is made from limestone, which is a naturally found material made from calcium carbonate, or CaCO3. Lime exists typically in two forms: the calcium oxide material, which is industrially known as quicklime, and a hydrated form known as hydrated or slated lime. Quicklime, or calcium oxide, is formed typically in kilns directly from limestone. It can then be hydrated by mixing calcium oxide with water. The hydrated form, calcium hydroxide, can be reconverted to limestone by reacting with carbon dioxide. These reactions form what is known as the lime cycle, which is visible on screen. For the purpose of our case study, we will only be looking at the production of quicklime. Quicklime has to be produced in a kiln at around 1000 degrees Celsius, or 1273 Kelvin. This is because under normal temperatures, the reaction isn't favorable. This can be verified by calculating the reaction equilibrium constant at both 298 Kelvin, which is ambient temperature, and 1273 Kelvin. First, we'll start with the chemical reaction, which can be seen on screen. And from this, we'll be able to get stoichiometric coefficients, and we can then reference thermochemical data to find Gibbs free energies and enthalpies of formation. Using this table, we can then calculate the Gibbs free energy of reaction and the enthalpy of reaction for the system, which is 131.23 kilojoules per mole and 178.4 kilojoules per mole respectively. These values can then be used in equation 1, explained before, to find the equilibrium constant at 298 Kelvin. As you can see, this calculated value is extremely small, indicating the reaction is unfavorable and will likely not even proceed at these conditions. Next, let's try calculating K at the modified system conditions when limestone is placed in a kiln heated to 1273 degrees Kelvin. This will be done using equation 2. For simplicity, we will assume the enthalpy of reaction is independent of temperature. As you can see, following the equations, the calculated value for K is now 8.870, which is much higher than previously. This is a much more favorable value, and the reaction will proceed. This value is likely higher in actuality, and in this example is lower due to the assumption that the enthalpy of reaction is independent of temperature. However, the concept is still evident. Based on the equilibrium constants, this reaction won't even occur unless it is subjected to a high temperature, which is why quicklime is produced in a kiln at 1000 degrees Celsius. This is just one example of when chemical reaction equilibrium constant can be applied to common industrial practices. Thank you for listening.